Hello again everyone, welcome back to ptet.chemistry channel. So in this new series of lecture tutorials, I'll be covering this idea on rate of reactions. So rate of reaction is also known as speed of reaction. It's to do with how fast or how slow a chemical reaction is actually going on. So in this topic, what is most important is this idea of collision theory. So in fact, when I was in university, collision theory is still a very important concept, even all the way up to university chemistry. So for two things to react, they have to collide. So imagine if this is your particle, and then this is another particle. If they are isolated in their own beaker, let's say in their own container, they are not colliding. But when you pour one into the other one, they will collide. They have to collide in order to react. No collisions. No collision means no reactions. But just because you collide does not mean that you will react, because sometimes they just bounce off each other. So you need to collide in the right orientation. So you also need to talk about the correct or the right orientation. Orientation means how are you arranged in space. As we know about particles such as enzymes in biology, they are very specific because they follow the lock and key mechanism. So this is a three-dimensional arrangement in space that they can only collide in a particular manner, in a particular fashion for the reaction to happen. The collision theory basically says that there is a certain amount of particles per unit volume. So if you look at this idea, per unit volume here, so this is in a three-dimensional setting. If I have a cube, and then in this cube, how many particles do I have inside here, inside the volume there? Which is why it's very important to think about concentration, mole per dm cube or gram per dm cube. In fact, it could also be gram per cm cube. These are your mass concentration from year 9. These are your molar concentration from year 9. Together, they both tell you how many particles you have per unit volume, because you can relate mole with the number of particles. As you know, that's related by Avogadro's constant, Avogadro's number, 6.02 times 10 to the 23. What is more important, however, is how frequent do they collide? Do they collide more frequently or less frequently? The next thing is to do with kinetic energy. We know that kinetic energy is to do with movement. So kinetic energy is affected by temperature. So temperature is a measure of average kinetic energy. That was your kinetic particle theory back in year 9 under states of matter. So temperature tells you how much kinetic energy your particle have. The higher the temperature, the faster your particles move because they have more kinetic energy. Last but not least is this new idea called activation energy. From the word itself, it's activation. So like I said earlier, for two things to react, they have to collide. That's the first condition. They must collide. The second thing is they must collide with the correct orientation. And then the third thing is activation energy. Must overcome. You must overcome the activation energy. So activation energy is this barrier that you have to overcome before reacting particles can collide with enough energy to react. So you might collide in the correct orientations, but they don't have enough energy. If they don't have enough energy, therefore, they will not have overcome, they will not have surpassed, they will not have enough energy to exceed the activation energy, which is the minimum energy required for reacting particles to have before they can undergo a reaction. Okay, so I think let's get started with this topic. So blah blah blah, this is talking about catalyst. We'll come back to this in a little bit, but catalyst is basically an English word. So catalyst is the noun. It comes from this verb called catalyze. This is the US spelling, and then the UK spelling is with the ZE. So there's the UK spelling. Regardless, both of these will give you the same noun as the correct spelling. So it's pronounced as a catalyst. When you pronounce it, it's catalyst, but when you spell it, it's C-A-T-A-L-Y-S-T. So both of these would mean to speed up the growth of a country, to catalyze the growth of a country, to speed up the development, to catalyze the development. So a catalyst, in the context of chemical reactions, it increases the rate of a reaction, it speeds up the rate of a reaction, it makes the reaction goes faster. What it does is it gives you an alternative reaction pathway that can alter the original activation energy actually doesn't change. It is about an alternative reaction pathway. So you have a choice. Alternative means you have a choice a choice in how you're going to conduct the reactions. And this alternative reaction pathway is a new and lower activation energy. And we'll come back to this later on when we discuss on catalysts. The bulk of this topic comes down to describing and also explaining. So the combined science students doing a much more elementary and introductory of reactions, they just need to describe. But in the pure science, pure chemistry curriculum, you're expected to describe and also explain, particularly using collision theory. Using collision theory, remember what we said about collision theory? They must collide. And then we must talk about frequency. How often do they collide? And we must also talk about their orientation, as well as do they have enough activation energy to react or not. Okay. In terms of changing concentration, so there is factor number 1, changing concentration of solutions, changing the pressure of gases, changing surface area of solids, changing temperature, using a catalyst or removing a catalyst, which include enzymes, as I mentioned earlier. You have learned that in year 9 biology. That is what you call a biological catalyst. They help to speed up your digestion in the body. They help to speed up decomposition of certain substances. Okay. We'll come back to these other two statements in the later tutorials where they are more practical based, and they will be linked together with some experimental tutorial videos that I'll show you eventually. So rate of reactions, what is actually meant by rate of reactions? I've talked to you about earlier where rate is about how fast or how slow reaction is going, but that is not the actual definition. The actual definition for rate of reactions is actually the change in concentration of a change in time. So this is important, change. It's not just a fixed thing, it's a change in concentration of reactants, but you could also monitor how the product concentration changes over time. Of course, the reactant will decrease over time, and then the product, as the reaction progresses, you will get more and more product over time. So concentration of product will increase over time. So in terms of this thing per unit time if I have to write that in the mathematical expressions, so what we'll get is rate is equal to change in amount or change in concentration divided by change in time. So it's to do with amount over time, but it's to do with change. When we look at this, the amount there could be mass, because you could be measuring masses, or you could be looking at volume of gas. So as we produce a gas, we can collect the gas and we can measure how much volume of gas has been produced. This thing here, change in time, is basically time. In terms of time, we can use a stopwatch. So a stopwatch will measure time in the lab. A mass will be measured by using a mass balance, as you know, an electronic mass balance in the lab. How about volume of gas? Volume of gas can be measured by using a gas syringe, and you have learned these in year 9 experimental techniques, as well as by using an inverted measuring cylinder. So we can have an experimental setup where we invert a measuring cylinder and we collect gas by displacing water, so we can collect the gas as it passes into the measuring cylinder. This is downward delivery. This is collection of gas by displacing water. This square bracket there refers to concentration of the reactant. So the reactant started with a certain amount and it will decrease over time as the reactant get used up. So we think about it, reactants get used up, and that is why the concentration of the reactant will decrease over time. However, this thing here, you get more and more products formed over time. That is why the concentration of products increases over time. However, we get this thing where it flattens out. Here the reactant get used up completely, but here we can see that no more product is formed. When it flattens out, no more product is formed because reaction has finished. So no more product forms. How do you know? Because it has come to a flat line. There is no more product that's being formed. Reaction has stopped. Reaction has finished. Reaction has stopped. Okay. So here is just a mathematical expression. So what we can do to calculate gradient, these are a curve, these are not straight lines. We need to draw a tangent. So this is very important, draw a tangent. This is a mathematical term, a tangent at that particular point, or at that particular time, because that is the time on the x-axis. When you draw a tangent, it's a linear line. And when you have a linear line, you can talk about gradient. So this is basically what the diagram above is showing. This is the change in y. So y2 minus y1 is equal to the change in y. So delta there refer to change. Delta means change. And then you also have x here on the horizontal axis. This is the change in x. This is x2 minus x1 equal to delta x. This is the change in x. So what we know about gradient is to do with the steepness of the slope. So we can say that this is steeper compared with this thing here. So this purple line is getting less steep, but I can go even steeper when I go that way. So we can say that the gradient becomes steeper going that way as it gets more and more vertical. And when you go further down, the gradient gets less steep. So here, the gradient becomes steeper. Okay, S-T-E-E-P there. The steeper the gradient, the faster is the reaction. Because the steeper it is, it means that there is a large amount of product formed over the same time. I can draw another tangent like this. So you can see that this green color tangent has a higher gradient compared to this thing here. And I can draw another pink one here. So towards the end of the reaction, as you could see, going this way, the gradient decreases. So it's very fast at the beginning, and then it slows down, and then it slows down even more as the gradient gets less and less and less steeper. It's the same thing on this reactant side. I can draw a gradient here. So that thing is steep, and then I can draw another one. Well, it's already drawn here, it's like that, but I can draw another one which is closer to the end here. So as you could see, the gradient gets less steeper as the reaction progresses because the reactant gets used up very quickly at the beginning and then slows down even more towards the end of the reaction until the reaction has stopped completely. Here the reactant gets used up. Here no more product is being formed. That's when you know the reaction has stopped. I wouldn't be too worried about the tangent theta, but what is important is the vertical change divided by the horizontal change in y over change in x, change in the amount, change in the concentration of the reactor or the product divided by change in time. That would tell you the rate of reaction. So as I mentioned earlier, the rate of a reaction, how fast a reaction is going, how much the concentration of a reactant or product changes over time, depends on the concentration of the reactants, depends on temperature at which the reaction takes place, depends on the use of catalyst, as well as surface area of reactant, which in this case, it clearly refers to a solid reactant that talk about surface area. And this concentration of reactant can be divided into two because you can also be talking about pressure, especially for gases, and they were stated in the syllabus. They are stated as two different factors. Concentration of solution as one factor, pressure of gas as another factor. If you had a look at the syllabus, concentration of solution is one factor, pressure of gas is a separate factor. So just make sure you know that when we talk about gases as well as solution, there are two different factors you can talk about that. Just a brief idea on what the collision theory is about. This is a reaction between hydrogen gas and bromine gas to give you hydrogen bromide. This is a gas and it's not in water because there is no water present. This is just gaseous reactants as well as gaseous product. So these diatomic molecule and these diatomic molecules come together and they react. They have to collide. You have to collide. That is the first rule of collision theory. But then you must collide with the correct orientation. So the correct arrangement in the space is called orientation. So how the molecules, how the reacting particles are arranged in space, and then you must have enough energy. With enough energy to surpass or to overcome the activation energy before you can have reactions happening. So basically that is what collision theory is about. You must collide with enough energy that overcome the activation energy, big E and small a, and you must collide with the correct orientation. So definition of activation energy is a very, very important definition. It's the minimum amount of energy that reacting particles or reactant particles, you can talk about reacting particles if you want to. So it's the minimum amount of energy that reacting particles or reactant particle must have. Instead of possess, you can talk about must have in order to react. So just because you collide with the correct orientation, but you don't have enough energy to overcome the activation energy, you are not going to have a reaction taking place. It is to do with an energy barrier that these reactants must overcome. You have learned a little bit about activation energy when you did chemical energetics. Chemical energetics was our last topic, talking about exothermic and endothermic reaction. This is an example of an energy profile diagram. So we have the reactants going to products. This is the progress of reaction. Sometimes they also label it reaction coordinate. So going from reactant to product, what is the changes, or what are the changes that is involved? You must overcome this barrier. So from the starting point to the top of the peak, that is called activation energy, one way or one direction arrow. So this is going up. Activation energy is almost 99% going up. So, and then from the reactant energy level to the products, so that means the reactant lose energy. This is technically not correct. We don't use a double-headed arrow. So make sure that you just do a single-headed arrow from the reactant to the product. That is your enthalpy change. This is going downward. So the reactant have lost energy in forming the product. So the enthalpy change is lesser than 0. That means it's an exothermic reaction. So that means the reactants release energy to the surrounding. So the system lose energy to the surrounding. Therefore, the surrounding will get hotter and the system will have lost energy. So activation energy is basically the energy that this reacting particle must have before they can overcome the barrier and undergo a reaction to form the products there. So in terms of the energy required, well, you do need the energy to break some bonds in your reactants. You need to overcome the repulsive forces, etc., etc. Okay, some reactions can go forward and backward. So we will be thinking about reversible reaction in our next topic. But in the meantime, I'll just show you this arrow. These are single-headed arrow. This is going from left to right. This is another single-headed arrow. This is going from right to left. This is a representation of a reversible reaction. Reversible means it can go both way, left to right and right to left. So when we think about forward reaction means from left to right, whereas backward reaction means from right to left, from products to reactant side. So if we're going from reactant to product, this is our activation energy from the starting point to the top of the peak. If you're going to the backward reaction, that's from the products to the reactant, so you're going this way. Your progressive reaction is going from right to left. So this is your starting point to the top of the peak. That is why that is called activation energy for the backward reaction, whereas previously this is activation energy for the forward reaction. Okay, I think I'll just leave it here since I already covered collision theory, and there's a very nice introductory kind of phase to this topic on rate of reaction. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Follow me at ptet.chemistry on Facebook, Instagram, Twitter, and Telegram to get connected. And in the next series of lecture tutorials, I'll discuss more describing and explaining the factors affecting rate of reaction in terms of collision theory and kinetic particle theory.